18, also the same thing. They want you to compute. They want you to find they want you to derive one identity, which is the second derivative of t of the integral of x squared times u squared. They want you to derive this identity equal to a times integral Rn du squared plus 4n, so on. Okay, 4n times integral of f of u squared times u squared minus f of u squared dx, a capital F of u squared dx. So you use A, and then B is to use A to show that there doesn't exist a solution of the cubic nonlinear Schrodinger equation existing for all time if this is negative for n greater or equal to 2. Okay, so how do we do it? Well, it's actually quite simple. All you need to do is just take derivative of the x squared, of the integral of x squared u squared, and then you write it out using our equations, okay, nonlinear Schrodinger equations, and you keep writing and using the vector analysis. Okay, and keep in mind you have, from time to time, you have to use divergence theory to throw away the complete divergence term. So after a while, so as you can see, from the very beginning, this part, d dt integral of x squared u squared, I keep doing it. Eventually, I got this negative 2 over I integral Rn x times negative gradient of u times u bar plus u times gradient of u bar dx. Okay, that's the last term, last line from this derivative. Okay, and then when I'm taking the second derivative of the second derivative of t, second derivative with respect to t of this x squared u squared. So I started from the last line of the last page of the previous page. So I take derivative of this very term. Okay, this very term. So I get, so I take a second. So I have second derivative of the Rn x squared u squared. So just write it out, take derivative inside it, and then use our equation, and just try to write a complete divergence and then throw it away. Okay, so I get this one, and then continuous working, and I guess lots of terms, but all these terms, it can be done. All this can be easily verified. Okay, so I get this divergence. Yeah. So I get this term. Let me just put it here. So 2 times. Okay, the last line reads 2 times the integral of Rn of x dot minus gradient of f of u squared u bar plus f of u squared u gradient of u bar plus gradient of the process of u times u bar, and so on. Okay, that's the last term. Okay, many terms, but that's fine. You just keep working on, and keep in mind, we have some identities. Before we go on, we have some identities. For example, like x times gradient of u, x times the process of u times gradient of u bar. I can write it as this times this, and using the integration by parts, I can derive the last line, x dot gradient. I got x dot gradient, x dot the process u times gradient of u bar is gradient of x dot gradient u bar times gradient of u minus gradient u squared minus this summation k from 1 to n, summation x sub j. Okay, j from 1 to n, x sub j. Okay, second derivative u bar partial xk, partial xj, partial u, partial xk. And likewise, for the x dot gradient u bar times gradient u, at that point u bar gradient u, I got a similar term. Okay. All right. And then, therefore, this particular term, x dot negative 2 gradient at the point u times gradient u bar minus 2, the point u bar gradient u is, eventually as keep computing it, it actually, you just do it carefully, and then eventually I got gradient of something plus 4 minus 2n quantity times gradient u squared. Okay. Therefore, if I substitute all this into the original equation, this is what I got. 2 times integral of x dot gradient minus f of u squared plus 2 times capital F of u squared, and gradient u bar plus u, and Laplacian, this is Laplacian u bar plus u, Laplacian u bar minus f of u squared minus 2 gradient, divergence of certain terms, and plus 4 minus 2n the square of gradient u. So I keep doing it. Keep in mind, I throw away all the terms that have complete divergence in it by using the divergence theory. So eventually, I got what we have, what we need to show. Okay, namely, the second derivative with respect to time of integral of x squared u squared is a times integral of gradient of u squared dx plus 4n integral of f of u squared times u squared minus capital F of u squared dx. All right. Then the important thing, how I'm going to use it. Okay. So this is particular case where little f of u squared is minus u squared, and therefore capital F of u squared is minus 1/2 u to the 4th. Okay, it's minus 1/2. Yes, integral of that, so 1/2 minus 1/2 u to the 4th. So little f of u squared minus capital F of u squared is minus 1/2 u to the 4th. Now, if e of 0 is negative, then from number 17b, that integral du squared minus u squared of u to the 4th over 2 dx is equal to e of 0, because that is a constant. Conservation of energy is less than 0. So the second derivative of t of integral of x squared u squared is less than 4 times e of 0. Keep in mind, e of 0 is a negative number. So when I integrate this term, okay, so I integrate once and twice, so I get the term where then it comes to integral of x squared u squared is less than 2e of 0 t squared plus c1t plus c2. However, the right hand side will be negative if t is large enough, okay, because the coefficient of e squared is negative. But the left side is always non-negative, so this is impossible. So this is contradiction. Therefore, u cannot exist for all time. Okay, so that's all the hint to number 17 and 18. Hope you enjoy it. I'm recording this from California. Okay. Have a nice break. Bye-bye.